Look at the end of your finger. Compared to the rest of the animal kingdom, it looks entirely defenseless. In contrast, most mammalian predators rely on curved, razor-sharp claws to dig, to fight, and to survive in the wild. But our primate ancestors faced a different survival challenge. They needed to silently navigate through dense tree canopies. Moving along small branches required wide, highly sensitive fingertips that could feel the bark and grip the wood, rather than aggressive weapons that would slip or make noise. If a fingertip is entirely soft, it fails at this task. When you press an unsupported pad of flesh against a hard surface, the soft tissue simply rolls backward. Without a rigid structure to hold the flesh in place, a firm, reliable grip is impossible. This cross-section shows how the flat nail solves the problem. As the finger presses down, force travels up through the flesh and bounces off the hard nail plate. Those force vectors redirect downward, locking the soft tissue in place to maintain structural integrity. This physical counterpressure creates what biomechanicists call an extended precision grip. That firm backing gives human beings our precise dexterity. It allows us to peel fruit, pluck a tiny seed, or hold a needle and thread. Human ancestors evolved this specialized precision tool to gain the mechanical control necessary to build the world. To understand how this tool is built, we have to look below the skin. Right at the base of your fingernail is a highly proliferative biological factory called the nail matrix. You can actually see the very front edge of it. It's that pale crescent-shaped area known as the lunula. This factory powers up astonishingly early in our development. The assembly of the human nail unit begins when we are just 9 weeks old in the womb. Its primary output is a structural fibrous protein called alpha-keratin. This is the exact same tough polymer found in the hooves and horns of other mammals. The secret to alpha-keratin's strength is an amino acid called cysteine. It acts as a chemical hook, forming microscopic connections. These links create disulfide bridges, snapping loose coils into an interlocking network. Like vulcanized rubber, this heavy sulfur concentration compresses the structure, granting immense rigidity. A relentless molecular assembly line engineers these hardened cells into a shield of living armor. This cross-section illustrates how the matrix compresses those hardened keratin cells into a highly organized 3-layer shield. You have a dorsal layer on top, an intermediate layer in the middle, and a ventral layer on the bottom, all stacking and pushing forward in unison. This biological assembly line absolutely never stops. As new cells are produced, they continuously shove the older ones outward at an average rate of 3.5 millimeters every single month. But this armor has a surprising flaw. Despite its rigid strength, the nail plate is actually far more porous than human skin. The composition of the nail includes up to 12% water, and it easily absorbs external chemicals. This permeability means that without some kind of defense, the sensitive tissue underneath the plate would be highly vulnerable to microscopic fungi and foreign pathogens. The body compensates for this vulnerability right where the nail meets the finger. A band of living tissue called the eponychium, which we often call the cuticle, grows out over the base to form a watertight biological seal. The human nail operates as a masterclass in structural compromise. It is a material rigid enough to protect our digits, yet so porous that it requires a constant, dedicated biological sealing system just to survive in the open air. Operating this keratin factory demands a staggering biological cost. The matrix requires a massive, uninterrupted supply of blood, oxygen, and nutrients to continuously push out miles of protein over a lifetime. Because this process is so resource-heavy, the nail becomes a real-time monitor for the rest of your body. Any systemic trauma, disease, or severe malnutrition immediately disrupts production. Medical professionals can read the shape of the nail to detect internal starvation. For example, a chronic lack of iron deprives the matrix of the oxygen it needs to build strong layers. The nail weakens and collapses inward, creating a concave, spoon-like depression in the center of the plate. Conversely, a chronic lack of systemic oxygen, which often points to serious lung or heart disorders, causes the tissues in the fingertips to swell. The nails respond by forcefully curving over the edges of the digits, a condition known as clubbing. Look at this clinical illustration. When a person suffers a severe illness or a high fever, the body goes into emergency mode. it temporarily shuts down the nail matrix entirely to reroute energy to vital organs. That sudden halt in production leaves behind deep horizontal trenches running laterally across the plate, known as Bowes lines. Because the nail grows at a predictable rate, these grooves act as permanent physical records of the exact days your biological factory went offline. The human nail is a specialized evolutionary technology. It gave primates the gift of precision dexterity, and today it serves as a continuous physical ticker tape recording our internal survival.